Hello, welcome back to es346 Basic Thermodynamics. This is module 2.2, topic is heat transfer. The corresponding sections in the textbook are Sengel and Bowles, section 2.3, and the special topics at the end of the chapter. Here are the learning outcomes for this module. At the end of this module, you will be able to identify the three modes of heat transfer, and you will be able to apply appropriate heat transfer equations to solve an engineering problem. So let's discuss the three modes of heat transfer. They are conduction, convection, and radiation. So let's talk about each one in turn. Conduction occurs when energy is transferred through a solid medium. So for example, imagine that you were to stick a hot poker into the fire and then hold it there for a while. Eventually the end would get hot. That is occurring by heat conduction. So imagine that's our poker, and one end is hot. On that end, heat would be transferred by conduction in that direction. The equation that describes heat transfer by conduction is the rate of heat transfer is equal to K, which is the thermal conductivity, A, which is the cross-sectional area that heat transfer is occurring, and then the temperature difference, delta T over delta X. So as I drew this bar here, there would be a cross-sectional area there. That is A. And then delta X would be the distance of that bar. Convection is another mode of heat transfer. And you notice this, for example, if you go outside on a windy day. So imagine here's a person standing here, and there's a wind blowing, and they would feel perhaps a heat loss if you're in Alaska, maybe a heat gain if you're down in the deep south. But there would be heat transfer by convection. The describing equation for convection is the rate of heat transfer is equal to H, A, T of the fluid minus T, S. So this value H is called the heat transfer coefficient. And it is a function of many things. For example, what is the fluid that is flowing, how fast it is flowing, and various other material properties. The third mode of heat transfer is radiation. And the most often time you notice radiation would be the sun. The sun is hot, it's hotter than the surroundings, and heat transfer occurs by radiation. The describing equation for radiation is the rate of heat transfer is equal to epsilon, sigma, A to the area, T of the surface to the fourth power minus T of the surroundings to the fourth power. So this equation is a little bit different. Here we have the temperature to the fourth power. It's also very important that we report that in absolute temperature. So use values of Rankine or values of Kelvin. Again, we have the cross-sectional area, and this value here, sigma, is called the Stefan-Boltzmann constant. It has a couple different values. They're fixed values. In SI units, it's 5.67 times 10 to the minus 8. And the units are watts per meter squared, Kelvin to the fourth. And in English units, that would be 0.17 times 10 to the minus 8. And the units here are BTUs per hour, foot squared, Rankine to the fourth. Both of those values you'll find in the back cover of your textbook. Let's talk a little bit about the material properties that occur. So on the left here, I have table 2.3 from the textbook, and I have the equation for conduction. And so this value K is a material property of what the heat is being conducted through. It's called the thermal conductivity. This table shows various values of the thermal conductivity, and if you notice right up at the top, we have a very large value, diamonds, 2300. It's very high because it's a very regular crystal structure. As you move down, you see there's metals on the order of a few hundred. And then you get down into things like brick and water, which are on the order of about 1. And then at the bottom, we end up with insulating materials that are around 100 or small. Another interesting thing is that these change by several orders of magnitude, from things that are called good conductors to things that are good insulators. On the table right over here, I have another material property, which is the emissivity. Remember, that is this value epsilon in the radiation equation. This describes how well photons are able to leave the material. And so you'll find out that there's a range of emissivities, but they are all between 0 and 1. So very low values of emissivity means that the photons are not able to leave the material very well. High values of emissivity means photons are able to leave fairly easily. So for example, if you look, black paint at 0.98 is a very good emitter of photons. That's why things like wood stoves are often black, because you want to be able to transfer energy to it. You see things like foil at 0.07 is very small. This is why you often see insulative materials to have aluminum foil on the outside. It cuts down on the rate of heat transfer by radiation. All right, let's talk about the convective heat transfer coefficient. This is the value H in the equation that we wrote before. H is different. It's not a material property. It depends on the mode of heat transfer, how it is happening. It's a fairly complicated thing to compute, but here in the table we show some typical values for free convection and forced convection. Now, what's the difference between free and forced convection? Well, if this was, for example, a hot surface here and free convection was occurring, the heat would just be sort of rising up off of it due to buoyancy. It's not a very good mode of heat transfer, and we realize that free convection tends to have smaller values. Gas and liquid is whether this fluid out here is a gas or whether it's a liquid. Now, in forced convection, that's, as you might not be surprised, would be when we're actually forcing the fluid across. So, for example, if the wind was blowing or water was flowing across it. This is a better way to move heat through, and we realize that forced convection values are even larger. The largest rates of heat transfer coefficient happen when you actually have boiling or condensation occurring. All right, let's go ahead and do an example problem. So here's the example. I have a wood stove. I'm told that it's 2 feet by 2 feet by 1.5 feet. It has a surface that is 400 degrees Fahrenheit. It's transferring heat into a room that is 75 degrees Fahrenheit. I want to know the total rate of heat transfer that this stove is delivering to the room, and we're told a value of H. So why don't you pause the video for a minute and think about what modes of heat transfer do you think are important for heat to be going from the wood stove into the room? Okay, well, hopefully what you came up with is that the total rate of heat transfer was equal to, we've got radiation and convection. So we're going to go ahead and add those two together. Now, one of the things, if you recall from the equations, is we need to know the area. So I'm told what the dimensions are, 2 by 2 by 1.5. So if we think it's 2 and 2 in that direction, 1.5 in that direction, we can find out what the total area is. And what that's going to be is, well, I've got a top that's going to be 4 square feet, a bottom that's 4 square feet, and then I've got 4 sides that are each 12 feet, so that's 20. So my area is 20 square feet. So now let's go ahead and write our equations here for radiation. We have the emissivity, Stefan-Boltzmann's constant, cross-sectional area, the temperature of the stove to the fourth minus T of the room. I'll just call that T sub R to the fourth. There's my radiative component, and I also need to go ahead and add my convective component, HA, T of the stove minus T of the room. Let's go ahead and plug some numbers in there. Emissivity, if you recall from one of the previous slides, stoves tend to be painted black because they're very good emitters, and so a value of 0.98 would be appropriate. Stefan-Boltzmann's constant, we're in English units here, so I'll do 0.17 times 10 to the minus 8. And now I've got my temperature to the fourth power. And recall, we need to do this in absolute. So now I'm going to be doing this in Rankine, which means I'm going to be adding 460 to this 400. So I'm going to have 860 to the fourth minus that of the room, which is 75 and 460. So that will be 535 to the fourth. That's my radiative component. Now I'll go ahead and put in my convective component, and that I was told was 5 for the heat transfer coefficient, an area of 20, and then a temperature difference of 860 minus 535. And in fact, I just realized I forgot to put my area in my radiation equation, So let's remember we need to multiply that with the top one by 20 as well. So now if I go ahead and calculate out what these numbers are, I realize that the radiative component is about 15,500. The convective component is about 32,500. So that gives me a total of 48,500. Oops, sorry, 48,000 complete BTUs per hour. So that's the net rate this stove is emitting energy into the room. Does it seem like a reasonable value? I was wondering. So I pulled up a brochure here for the Blaze King, the King Ultra version, and if we look at the constant heat output on high, we have a value that's 48,065 BTUs per hour. Surprisingly good agreement. All right, let's continue with this example and look at and answer this question. What's the temperature inside the stove? We're going to assume that the stove is made of iron. So here, what we're looking at is conduction through the wall. So if I was to kind of blow up and imagine that this is the wall of my stove, my room is, the surface over here, is 400. That's the temperature of the outside surface of the stove. There's going to be a temperature inside that is going to be something larger. So this is the inside of the stove. This is the outside of the stove. So here what I have occurring through the wall of the stove is a conduction problem. So we have the rate of heat transfer, which we calculated just now, at 48,000 BTUs per hour is equal to K times A delta T over delta X. So I need to know what the thickness of the stove is. So let's just go ahead and assume it's about a ½ inch. And what we're going to solve for now is delta T. So delta T is equal to, I have my 48,000, and then I need to multiply that by the thickness of the stove. It's about ½ inch. I'll divide that by 12 to keep my units consistent at the feet. And now I need to go ahead and divide that by my conductivity. The conductivity of iron is about 45. The units of that are going to be BTUs per hour, foot, degree Rankine. And then my cross-sectional area that we had from the previous part at 20 square feet. And if we go ahead and calculate this, we realize that's equal to about 2.2 degrees Rankine, which is the same as 2.2 degrees Fahrenheit, because we're talking about a temperature difference. So that means that the outside of the stove is at 400, the inside of the stove is simply 402.2 degrees Fahrenheit. That's not surprising. When you actually want a stove, you want to get the heat out of the stove into the room, so you want something that's a very good conductor.